Welcome to The Explainer. Today, we're diving into this really fascinating research paper that kind of pulls back the curtain on how we can measure and, more importantly, manage the quality of the software that pretty much runs our entire world.
All right, let's kick things off with a number, 40 to 80%. Any guesses what this might be?
That, right there, is the percentage of a software project's entire cost that goes into just keeping it running, into maintenance. And that number is directly and often painfully tied to the quality of its source code.
And what this really shines a light on is this huge, kind of hidden problem in the tech world. You see, bad code isn't just an annoyance for developers, it's a massive financial drain on companies and projects, year after year.
So, okay, if we're going to tackle this problem, we first have to agree on what we're even talking about. What is good code, anyway? It's a tricky question, right? Because quality can feel so subjective, so hard to nail down.
And this is where the paper offers a really solid, practical definition. They're saying, look, quality isn't some mystical, artsy thing. It's about tangible stuff. Can you read it? Can you maintain it? Is it reliable? These are the things that actually drive up those maintenance costs we were just talking about.
Right. So we have a definition. But how do you actually measure something like readability or maintainability? How do you put a number on good?
And you know, it's not like people haven't tried. But as the research points out, a lot of the existing models and standards, well, they've struggled. They're often out of date, or they're missing key pieces, or they're so specific to one programming language that you can't really use them everywhere.
Okay, let's just take one piece of the puzzle, complexity. I mean, we all know that when code is just a tangled mess of spaghetti, it's a total nightmare to maintain. But where's the line? When does it go from being just a little complex to way too complex?
This is where we get something super concrete. It's a metric called cyclomatic complexity, which is a fancy way of saying it measures how tangled the code is. You get a score. If it's between 1 and 10, you're in the green, low risk. But once you start climbing past 20, you're getting into a high-risk zone that's going to be a headache to maintain.
So clearly, the old ways weren't cutting it. The researchers knew there had to be a better system, one that was flexible enough for all the different ways we build software today, and one that could connect those big ideas, like keep it simple, to actual hard numbers.
And here's the brilliant part. The big idea was to stop looking at all these metrics in a vacuum. Instead, let's build a bridge. Let's directly connect the qualities we care about, like making our code easy to maintain, to things we can actually measure with a tool. And here it is. This is the model they came up with. You can see how it works, right? It links these big goals, like maintainability, to very specific metrics with super clear thresholds. We just talked about cyclomatic complexity. You want to keep that under 10 for good testability. But look at these others, like coupling, which measures how tangled up different parts of your code are, or depth of inheritance. The model says, keep those scores low, and you'll directly improve how maintainable your code is. It's like a practical checklist for quality.
So this all sounds fantastic in the lab. But the million-dollar question is, does this thing actually work in the real world?
To find out, the researchers basically set up a showdown. They grabbed two real-world open-source projects right off of GitHub. Project A was one of those projects everyone in the community loves. It's seen as high quality, it's well taken care of. Project B, well, let's just say it didn't have the same reputation.
And you don't have to take their word for it. The GitHub data tells the whole story. Project A, it's got over 100 stars, a bunch of contributors. It's alive. Project B, crickets. 0 stars, 1 contributor. The community had already passed its judgment.
So the test begins. They run both projects through the model, and boom, the differences are just night and day. First up, lines of code. Project A is incredibly tight and concise. Project B is way, way bigger.
And remember that cyclomatic complexity metric we talked about, the tangledness score? Well, Project A gets a super low-risk score of 2. Project B, though, hits a 20, putting it right on the doorstep of being high risk. Another massive difference.
So yeah, the results were just crystal clear. Every single metric pointed to the same conclusion. The model worked. It wasn't just guessing, it objectively confirmed what the entire community already knew. Project A was, quantifiably, the higher quality project.
Okay, so what's the big takeaway here? What does this all mean for those of us actually trying to build better software?
What's great is that the paper boils this all down into some really practical, actionable advice, and it all stems directly from what the model measures. Keep things simple.
Don't repeat yourself. Keep your classes and interfaces small. And this one's huge, automate your testing. These aren't just nice ideas. They're concrete steps to improve your metrics and slash those long-term maintenance costs.
And at the end of the day, that's what this is all about. The researchers make it clear. This isn't about chasing perfect scores for the sake of it. It's about a much bigger goal, building products that are reliable, effective, and actually serve the people who use them.
So what this research really shows us is that code quality doesn't have to be this vague, artsy concept. It's a discipline. It's something we can manage and measure. Which leaves us with a really important question to think about. In a world that completely runs on software, is settling for good enough a risk we can really afford to take anymore?